everybody for joining us today. We've got a great panel here, so we'd love to welcome up on stage Tal David, Bharath, Kannan, and Chris Ballance. So what I'd like to do is I'll give a brief intro on myself and then the panel, and then I'd love to give them each sort of, sort of call it like sort of 7-8 minutes or so. Please tell us about your company and tell us about the sort of the technology and what differentiates it from other stuff out in the market. So my name is Damien. I'm a partner with Morpheus Ventures. We're a Los Angeles-based venture capital fund investing sort of late seed through Series B, Series A being our sweet spot. We're a generalist fund. We have 3 portfolio companies that are in the quantum space. We invested in Rigetti Computing, Q Control, and most recently in a company called Coherent. Anyway, I'll pass it first. We'll go down the line, starting with Chris, who's CEO and co-founder of Oxford Ionics. Anyway, please take it away. Tell us a little bit about your company, maybe the origin story, and then what differentiates you from other Ionics companies.
Yeah, awesome. Great to be here. Oh, wow, there's a bit of feedback there as well. So we have a couple of core beliefs at Oxford Ionics. So we build electronically controlled trapped ion quantum computers. And our founding beliefs are really that if you want to build a quantum computer, you better have something that you really can build out at scale. And that means using the right tools that allow you to scale out the technology. And the second is that errors really are king in quantum computers, right? You really need to be able to reduce the errors massively. And this means a couple of things. It means, obviously, error correction in the long term. But what really drives how practical error correction is how low the physical gate errors are. And what drives how useful the systems are in the near term is how low your physical gate errors are. So we build our systems out of trapped ions. And ions, like atoms, are pretty awesome systems. The physics of an atom is really well understood, which is why we build atomic clocks out of atoms. And the problems with pretty much everyone else's approach to atoms is that you have to use lasers. And anyone who's ever worked with a laser knows that lasers really suck. So they suck for a couple of reasons. They're noisy, they're hard to build. But most of all, you can't really do stuff with them at integration scale. Integrating laser sources or laser modulation or laser distribution into anything that you can build at scale is really hard. However, if you control things with electronics like we do, you can build out stuff that you can integrate into a standard semiconductor fab. So what we're doing is we're building out systems where we can integrate absolutely everything we do into a chip that can be built in a standard semiconductor fab. And we're doing this with Europe's largest semiconductor foundry, Infineon. So like this, we've shown that we can get gate error rates that are comfortably beyond the state of the art. So we're now well below 10 to the minus 3 error per 2 qubit gate, and we've got some results we're going to be talking about early next year, showing we can go comfortably beyond the state of the art on that. And after that, it's all about how you build things out at scale. It's about how you build out larger and larger devices, how you manage any-to-any connectivity. And a lot of the devices we're building out now are towards our 256 qubit architecture. And we're really interested in speaking to people who want to see what they can do with these kind of systems. So we can build out to 256 qubits with any-to-any connectivity, and we can get errors down towards 10 to the minus 4 error per 2 qubit gate. We've already shown a long, long time ago that we can get our coherence times out to tens of minutes, and we can get single qubit gate errors down into the 10 to the minus 7s error per gates. So really, it's now all about the integration and the scaling.
Very good. And maybe actually well, I'll stick with the trapped ion theme and go to Tal David next, because he's in the sort of same modality or doing slightly different stuff. But Tal David is founder and CEO of Quantum Art Ltd. He doesn't sell out NFTs. There's another company by a similar name, just to be certain. But Tal, please tell us about your company and your points of differentiation in the technology.
Yeah, thanks, Damien. So I'm Tal, and I think that lasers are awesome. Right? So we started Quantum Art as a spin-off from Weizmann Institute of Science in Israel about a year and a half ago, actually a year ago, since we actually started working after raising our seed round. And our approach is a little bit different, looking at making the most out of the physics of the system rather than going to a brutal engineering path, which will need to be done eventually, but it's better to utilize the physics at the beginning. So we are combining building traps that can hold a large number of ions with coherent control tools to make sophisticated gates, to make robust gates, to all sorts of noise sources, and so on. Earlier this year, we published our large-scale multi-qubit gate method, which brings together massive amounts of qubits, tens of qubits at a time, to make complex gates that can save up on coherence time, waste on errors, and bring together many, many sequential small-scale 2-qubit operation into one large operation. And more recently, a few weeks ago, we published a few aspects of our scale-up strategy, which relies on taking this large-scale gates and implementing them on a highly configurable trap, which is a basic pole trap, but with a very long chain, segmented with lasers, into different segments that are decoupled with no crosstalk between them from each other, and so they can work independently and in parallel to each other. And because these are optical segmentation fields, we can turn them on and turn them off at will, and so we can rechange the configuration from one code line to the next code line without needing to shuttle ions around, without needing to do very low efficiency optical interconnects, and with the ability, because we control the configuration, to distribute entanglement massively across the whole QPU, and utilize really the all-to-all connectivity as we scale up to larger and larger numbers. We very much believe that we do not need to reinvent the wheel wherever it's not a must, and we believe in collaboration. And so one of the first things that we did after forming the company is drive and lead and approve a large governmental grant, consortium grant in Israel, which brings all the Israeli ecosystem together with some of the players that have been here, like Classic or Kedma or others, so that we keep to focusing on our core and bringing very good assets into our system development where we can, so we keep it nice and lean and flexible.
Very good. And we've got Bharath Kannan here, who's CEO and founder of Atlantic Quantum. And so you're in a different modality. You're in the superconducting field. Please tell us about what you're building and how you're looking to differentiate from the others in superconductors.
Yeah, I guess I'm the odd one out here, but superconducting qubits is, I'm sure everyone here knows, has been one of the leading platforms for quite some time, with heavyweights such as Google and IBM investing lots of time and money into this. And so, at Atlantic Quantum, we're a spin out of MIT, and the workhorse for the superconducting qubit community for the better part of well over a decade at this point has been the transmon, right? This came out of academia around 2007, and there are lots of nice things about the transmon. The nicest thing is probably that it's the simplest superconducting circuit that you can make that will act as a qubit, and that simplicity is really great, especially when you're testing things out at a smaller scale. Particularly in the academic setting, but even as you start to go up to a few qubits, tens of qubits, maybe even hundreds. But that simplicity really comes at a cost. And the cost is twofold, and it was already mentioned earlier. Basically, these types of qubits are rather susceptible to errors, and there are certain properties that we believe will make it extremely hard to scale up to the tens of thousands, hundreds of thousands, or even millions of qubits that we're going to eventually need. So we use a different type of superconducting circuit called fluxonium. Now, the fluxonium qubit is a slightly more complicated circuit. It adds an extra inductor compared to what the transmon has. And in fact, it's actually been in academia and the superconducting circuit field for quite some time, early 2010s, but really only started getting a lot of attention in the last, say, 4 or 5 years. And a lot of that attention has been towards the lifetimes of these qubits. So superconducting circuits, particularly the transmon, state of the art was around 100 microseconds. And now with these fluxonium qubits, we're able to very easily get up millisecond coherence, right? So for superconducting circuits, given the gate speeds of 10, 20 nanoseconds for single qubit and tens of nanoseconds for 2 qubit, this is really good. But only until recently, actually, we had a paper that we put out a couple of weeks ago. For the first time, fluxonium was not only just better in terms of coherence. Coherence is great, but ultimately what matters is the error rates, right? And we showed in our paper out of MIT, which then got spun out into Atlantic, error rates lower than 10 to the minus 4 single qubit, and error rates well below 10 to the minus 3 for 2 qubit gates. And this is averaged, right? So this isn't really cherry picked. It's really robust. So that's one side of the equation. And I think if you're going to pitch a new type of qubit, particularly one that is not nearly as mature as the transmon, which has so much time put into it, that's the baseline, right? It needs to be better at the very least before you do anything else. But you really need to, in order for it to be compelling, to switch from such a workhorse such as transmon, you really need to go beyond that. And one of the key features of fluxonium is this low frequency nature. Now, typical transmons operate at around 5 gigahertz, right, in these microwave regime. The fluxonium qubit operates at around 100, 200, 300 megahertz. There's a broad spectrum, but the ones that we use are around 1 to 300 megahertz. Now, that lower frequency is actually what eventually leads to the higher coherence times. But there's another added benefit, which is that the generation of the control signals is significantly simpler for these lower frequency signals at around 100 megahertz compared to the infrastructure you need for a many gigahertz signal, right? And this isn't just in the kind of electronics themselves, but also the supporting infrastructure, the cabling, right? All of these constraints become significantly relaxed when you reduce the frequency of your control. And so, what we're basically doing with this fluxonium is not only pushing the boundaries of what's possible with these error rates, but we're also doing it in a way where the ability to scale these qubits will be significantly simpler than what is possible with the transmon, both in terms of the complexity of what is required, but also cost, right? Because cost per qubit is something that we don't often think about, but if we're really going to build these fault-tolerant quantum computers, we're going to need to get there. So that's kind of the founding thesis of Atlantic Quantum, is we really want to focus on these two problems, and you need to do both simultaneously.
Very good. And just follow-up question there. Are you, when you say you're sort of scaling down the complexity of the control circuitry, is part of what you're doing, kind of moving part of that into the fridge, or is it just like everything that's outside the fridge is also just a lot simpler?
Yeah. So at a very base level, if you change nothing today, right, you already get the win in terms of the lower frequency. So even if you keep the room temperature electronics, it's already better, right? But as you mentioned, if you're trying to build a 1 million qubit system, we're not going to have 1 million cables going inside of a dilution fridge. It's just not going to work. And so fundamentally, you need to be able to co-locate the generation of the control signals with the quantum processor itself. And there's several approaches to do this. Probably the most mature one is cryo-CMOS, right? So there are people looking at the cryo-CMOS and putting the AWGs and signal generators at 4 Kelvin. And then sending that down to the millikelvin. There's certain issues with cryo-CMOS, which is that there's still a lot of heat dissipation, right? And you don't have that much cooling power at 4 Kelvin. I think typically it's in the watts scale for the pulse tubes that we have today. But you're probably going to need kilowatts of cooling power if you're really going to have a 1 million qubit processor running on cryo-CMOS. So then the question is, okay, that's maybe that'll get us a little bit further, but the math doesn't really seem to work out there. Can we take it one step further? And to that point, can we use superconducting circuits to actually manipulate superconducting circuits? Now, a common the next step is this SFQ technology, right? Particularly, a lot of people. There's been a lot of work looked into this RSFQ logic family. Now, those types of circuits can be pushed to, because they have much less dissipation, to lower and lower temperatures, but they still have quite a bit of loss, and there's quite a few issues with them that reduces the gate fidelities of your operations. And the thing is that whatever, like anything you do in terms of scalability cannot sacrifice gate fidelity, right? You have to maintain and even improve the gate fidelities as you do this co-location. And one of the kind of key constraints with the transmon, for example, again, is this high frequency nature. And because of the 5 gigahertz pulses that you have to generate, it limits you to these technologies such as RSFQ that can support such a high kind of clock to then create pulses of that order. So if you have a lower operation frequency, right, there are other kind of logic families that effectively approach the Landauer limit for computation, right? And I don't need a very complicated classical computer to control my quantum computer. I just need a DAC, right? I need to send digital inputs in from outside my fridge, and then I want those analog signals to be sent to my qubits. And so if I have this lower frequency qubit, this gives me quite a few options beyond RSFQ where you have much lower dissipation, basically approaching the limit of dissipation lists that can actually truly be co-located with the quantum processor. And one kind of key point here is that people say, okay, you lower the frequency of your qubit, you're going to make your gate times correspondingly longer. So do you really win? But we've shown in the paper that we published is we basically maintain the same gate speeds that you have with transmon. So a few tens of nanoseconds, single qubit, and like 50 nanosecond 2-qubit gates. So there really is kind of no downside to this approach, other than the slightly more complicated circuit that you have to fabricate. But if you can show that you can reliably do that, then this is, in our opinion, the path forward.
Okay. And so I guess, Chris, this question will go to the rest of you as well, but you guys are sort of, you're in fields with some fairly well-capitalized first movers. You're all trying to be fast, sort of second movers here. What advantages does that give you? Also, I guess, any disadvantages that you need to be aware of in your roadmaps?
Yeah, well, they always say the pioneers get the arrows in the back, and then the settlers get to keep the land. And that's how we see, I think, the world of trapped ion computing going out. We wouldn't be able to do what we have to do to scale out our systems if IonQ and Quantinuum hadn't built out their roadmaps beforehand. What they've shown, which is building really high-quality, small-scale trapped ion quantum computers, is how well the trapped ion modality works in these small systems, which means we can come in with a story of how we're going to say, well, these small systems are cool, but you really want hundreds of qubits to thousands of qubits in a platform where you can really scale these things. And we can only kind of put our nose to the grindstone and work on these problems because of IonQ and Quantinuum coming before us and doing that. So far, we see mostly upsides, having people who've shown the basic modality and the basic platform works, but also where you see them struggle with different technical problems is really a very valuable way forward. And I think what we can learn from both IonQ's and Quantinuum's trajectory is that if you want to build a 10 or 20 qubit quantum computer and get really high performance, trapped ion control with lasers is the way to go. But what's also really clear is that if you want to scale this out to hundreds or thousands of qubits, you need to do something different. You can't just put more and more optics down, more and more hand-aligned bits of stuff down, more and more laser beams skimming across the surface of the chip. This really limits how you can lay out your chip, how you can operate the chip. And if you can turn all of these things into electronics, you can really get rid of all these problems.
Yeah, I just want to second that statement there. I mean, we stand on the shoulders of giants, right? And in the superconducting qubit community, this is, for example, Google and IBM. And I think, okay, obviously as a startup, we always need to differentiate ourselves and say how our technology will get to the endpoint of a fault-tolerant quantum computer. But the wealth of information that they have kind of developed and shown to the community, right, has been extremely beneficial in even ourselves defining our own milestones. So I mean, for example, I'll say you go back to 2019 to Google's quantum supremacy experiment, and the highlight was the supremacy. They did something faster, right? And actually, in my opinion, the supplemental information of that paper was significantly more impressive, right? If you go and look at the actual hardware, 53 qubits with tunable couplers back then in 2019 was a massive step forward compared to what was at least publicly shown before. So this, that sort of game-changing step forward, gets then, people's brains really thinking about, okay, how are we actually going to scale this, right? Because it clearly works, right? There's a path forward with this technology.
Yeah. And I think the other interesting thing here is the way you build an organization changes depending on your long-term goal. Yeah. So being a second mover, when you can really see how you need to build out a company to deliver on the long-term promise rather than just focusing on the short-term promise, allows people like us to be able to come in and build out structures that are going to take us all the way to the end of the marathon, rather than that are in the sprint mode to try and show something, which gives us a lot of advantages on how we structure our company.
Right. I think that when you're head jumping into the pool, you better make sure that there is water in there.
Yeah.
So these guys have made sure that the pool is filled with water, and now we can go and refine, as Bharath said, refine our differentiation, our strategy, our unique capabilities, and learn from what they're doing in order to improve and go farther along. And I think that, at least in trap ions, where you don't need ultra sophisticated fabs, at least not in the beginning, it's less about capital intensive field, and it's more about know-how and making the most out of the platform. And therefore, the gap for now is not that huge, and I think it's a very good timing to be in that second wave.
And do you, Tal, how do you look at sort of, partnerships? I mean, being in an established modality presumably means that there's a bigger ecosystem for you to be able to kind of, not just simply learn from people that went ahead, but actually sort of, partner with companies that have solutions so you don't have to build them yourselves, right?
Right. So as I said before, we very much believe in collaboration. And if there are smart people out there making the control electronics or some software layers for error mitigation or circuit optimizations that I don't need to do it by myself, I'd rather either procure it from them or work with them even better and focus on the core. The mission is complicated enough, and that's true for any modality, that you don't want to waste your time and energy and resources on stuff that you don't have to. And especially in this day and age where we are still, as was said earlier today, not even in the first inning of the game, we have a lot to collaborate before we really start to compete. And I think that every new impressive result, like what we've heard from some people here in the conference this week, is driving the whole ecosystem forward. And I think that it helps everyone on the way. So if we can be focused and get help from friends to integrate and lead us forward, I think that's the way.
Okay. Sort of staying on the same theme of leveraging partnerships, I mean, maybe sort of, Bharath, how do you think about, software? So are you, does it make sense if, you guys are all focused on better hardware, but, do you need to be doing the software in-house, or how much of the software do you need to be doing in-house?
Yeah, I mean, as a startup, you have to pick and choose your battles, right? We don't have the resources that certain other players in this field have. And so the way that I think about it is, one thing is that there's no standardization in this field yet, right? And that's where it becomes difficult for people to use kind of software that is provided by someone else, because your system is somewhat custom and requires some care to actually deal with. That being said, you also don't want to. I think doing the whole full stack yourself at this point is just it's too expensive, and you don't need to, right? There's a lot of really smart people that are thinking about these platforms, ions, neutral atoms, superconducting qubits, and really focusing on that. And so you need to strike a balance between these two things. And from our perspective, we see that the hardware provider for now will at least need to develop, the firmware, right? The pulse level. We know our systems best, right? And layers higher than that could be taken care of by other players. Now, this will change as a function of time, right? As there's kind of more, people coalesce along a certain path. Now, whether there might be multiple modalities that kind of make it as time progresses. There may only be one, maybe there's none, right? We don't know. But as there's more standardization that's built in, This will, I think, make the chip providers, the back-end hardware providers, give them the ability to let go of more and more, right? And I think this applies to not just software. This applies to like the whole stack, right? The fridge. Right now, the fridge is kind of a commodity, right? We've gotten to that point because the community has agreed upon a certain level of performance that is required, and configurations. There's still some differences, right, when you go from provider to provider, but there's been enough time for people to coalesce. And the next step will probably be these cables, for example, right? There's many, many different ways of cabling up your quantum processor with superconducting qubits. And when you have this lack of standardization, this is also part of the cost driver, right? You don't get the benefits of economies of scale. So whether it's software or hardware, I think we're going to start to see this ecosystem build around where people will settle into their areas of expertise. You'll still have likely the Googles and IBMs and Continuums. They have the resources to do it all in some sense. But I think we'll see less and less of the all of the above approach as time progresses.
So I agree. Like any company is defined not by what they do, but really what they choose not to do. Right? It's very easy to dilute your effort and try and do a little bit of everything and not generate any value. And I think anyone really should have a laser-focused view on what thing they're doing of value, and then everything else you can buy in. And with I think most quantum compute modalities, but especially the trapped ions, the qubits over here, they just work. You're not going to do anything really to improve those. Anything you do makes those worse, and it's your job as a hardware provider to not screw it up so badly as you scale. Ethernet, pretty well defined, and definitely is going to be what the outside things. And all the stuff that sits between qubits and Ethernet, that's where the value really is in quantum computing. It's really about system integration and how you build up those stacks, and then how you work out where the boundaries and where the interfaces are in there that you can buy in external stuff, and where you have to vertically integrate and optimize. And especially in the near term, when we can't say we're going to throw away an order of magnitude performance in our qubits to use commercially available tools, until there are those well-defined standards interfaces, we really do just need to vertically integrate the most valuable and critical parts.
So we've seen some different approaches in the industry in terms of when to start talking to customers, usually government customers at first. How do you guys sort of look at this? It's like, North Star's fault-tolerant system, and you don't want to be talk to customers till then, or are you actively looking for government customers, for private enterprise customers as well? I'll start off with you, Tal.
Yeah, thanks. So I think it really depends on the customer. In my previous life, I was the head of a national strategy program. So I come from government, and I know how they think.
We won't hold it against you.
No, I'm free. I'm a free man now. Thank you. And I think that governments understand the significance of the field. They have a problem betting on a specific technology, and so many times you see governmental initiatives get split into tiny bits. So if you're a very big country, then the bits are big enough. If you're a smaller country, the bits don't amount to a critical mass. And so I think that talking to governments from day one is important because it helps them to drive processes forward. About private sector customers, I think that you can differentiate between two phases, let's say. The first phase is let's convince the enterprise customer that it's worth making the effort and making the investment. It's not clear for them that it's worth the hassle. And in order to do that, there's a lot of even pen and paper and simulation stuff and joint use case development stuff that you can do from day one. But on the other hand, the other aspect of doing real practical implementation, I think we should be very careful from overhype, and we need to really set the expectations in the right way, and therefore you need to be able to deliver what you promise. And then from that aspect, you should take your time and be ready before you actually drive private sector communications above this feasibility layer, I would say.
Yeah.
Bharath, how do you look at it?
To I guess just quickly tag on to that last point, something I like to say is that your most valuable asset is not your technology, it's your credibility, right? Because that is, if you lose your credibility, that is something that is very hard to impossible to get back. Whereas, technology is something that always progresses if you keep working at it. So I think as a community, it will be very important for us to not overpromise, right? I mean, you always want to overdeliver, right? And not overpromise and underdeliver. So from that perspective, at Atlantic, our North Star is fault tolerance, right? And the fundamental truth is that fault tolerance will take time. It will take probably longer than we even expect. And so it's, you say, okay, you can engage with, these big enterprise customers. We obviously engage with theory collaborators to think about, what are things that, if you have if we say we can give you this performance, what are the things that you can work on, right? But I don't think that we should go out and say that this is something that's going to generate value, right? Yet. I mean, obviously we want to get there, but that's a very high bar that we must be absolutely sure about before we go out there and make that claim. Now, there's also this, notion of NISC, right? Everyone's always talking about NISC. Personally, I haven't seen anything in the NISC regime that's really seems to be of value. That isn't to say that I don't want NISC to happen, right? I think if we would all agree that if someone came out with a NISC algorithm, this would make our lives significantly easier, right? And maybe it will, right? But it's very hard, especially as a startup. Again, you have to pick and choose your battles. It's hard for me to say I'm going to optimize my system for a NISC algorithm without really knowing that there's a payoff at the end, right? In terms of something useful. And so to kind of add to that, if you're on the path for fault tolerance, I mean, that's a higher bar than probably what's required for doing something with NISC. And so if something comes while you're on that path to fault tolerance, you'll probably be able to pick it up. And I guess going back to what was said a bit earlier, I think the government's probably the most important partner in this. These types of technologies where you're post-academia, where we're clearly beyond the ability to do something scalable and useful in an academic setting, but we're very much pre-business, right? We are R&D corporations. That's what we're doing, and the government has a huge part to play. And I mean, they've played an instrumental part in getting us to where we are today, right? And that's going to continue to be the case probably for at least the next decade. And so, when you say partner with the government, that may not necessarily be you're actually running some optimization for their logistics for something, right? Right. I think it really is.
There is a conversation sometimes where about if you're getting them to fund a certain roadmap, it needs to be a roadmap that works for you as well as for your government customer, right? So that trying to figure out that symbiosis.
Exactly. The question is always, why should you speak to a customer, right? And obviously, in the long term, we want customers who can pay us a really significant amount of money to do really significant things for them. If you're got a customer who's paying a not very significant amount of money for you to do not very significant amounts of things in there, you then have to really think about how much you want to optimize for getting that near-term revenue.
It could be a distraction.
Versus the long-term stuff. And it's very easy to then get distracted by playing around in the rock pools rather than go out into the ocean and actually generate long-term value. So finding the right balance of not getting disconnected from what your customers really want and working out what your customers want and then doing that, but not getting distracted by spending lots of time educating people about what they want out of quantum computers when the answer is you want a large quantum computer. Be that, be 1,000 qubits with 10 to the minus 5 errors before fault tolerance, or 100,000 physical qubits and a few hundred logical qubits post-fault tolerance. It's not going to be a 20-qubit system.
Yeah.
So if you're playing around with a customer doing something on a 20-qubit system, you better be getting something valuable out of it yourself.
Yeah, and to kind of tag on to that, it takes a lot of time and money to put out a system, right? This isn't just okay, I have this system and then the next day someone can program it, right? You have to develop a whole framework around it to make it accessible by others. And that's a lot of time and money that could be spent on actually pushing the needle forward on the fundamental hardware. And so that isn't to say that there is no value in doing that, right? There is, one can make the argument that from an education perspective, both at the student level, but also educating the general population of the potential of this technology. There's value to be had there, right?
Exactly, but it's better for someone else to do it.
It's better for someone else to do it, right? So an IBM who has the resources to really invest in that, they can extract that value. They can do it well, right?
Exactly. This is a second mover advantage yet again.
Exactly.
So bearing in mind we're running, we got a couple minutes left, but I think you've got over $50 billion allocated by governments for quantum, and I'm going to mix apples and oranges a little bit here, but you got 50 billion allocated by governments on the one hand, and I think last year there was 300 million spent by private enterprise on proof of concept projects in quantum. So clear discrepancy between the two. But as you look down, in the near term, and by near term I mean like next 24 months, do you see any sort of flywheel dynamics where enterprise is going to start to sort of invest more in quantum beyond just kind of the dabbling that it's been doing? Because they're starting to maybe get enticed by some near-term value in applications. That's sort of.
So I'll take that since I have a very simple answer.
We're down to a minute here.
No.
Okay. Bharath?
24 months, I think not.
No. How about you, Tal?
I think they will help each other. Enterprise will not go there if government is not there, and government needs to see that someone cares. So they need to work together. But I agree with these guys.
And that's not to be negative, right? The flywheel is starting to spin up. People are starting to do that. But the core thing we're all here to do is to build better and better quantum computers. And we want to be working with people to really understand what they want out of these systems and how we get there, rather than focusing on trying to milk near-term revenue that not covering the cost base and trying to worry about that.
Very good. Well, Chris, Bharath, and Tal, thank you very much. This has been a great panel, and hopefully the audience really enjoyed it too. So.